Hello and welcome back to 15-Minute Math. In our last video we defined the derivative. So remember, the derivative is just the rate of change of a function at a particular point. So we're thinking about the slope of a function at a particular point. And that was troublesome for early mathematicians, before Newton and Leibniz came around, because for any function that's not linear or constant, that slope's going to be constantly changing. Let's look at this red graph here. The slope of that line, or the slope of that curve rather, is different if we look at the slope here. And whenever I say the slope of that curve, really what I mean is if we would draw in, say, a tangent line, kind of like so, what would be the slope of that tangent line? So when I say the slope of the curve at that point, really in my head, that's what I'm imagining. I'm imagining drawing a little tangent line and then thinking, okay, well, what's the slope of that tangent line? But that would be different depending on where we drew it, right? That slope is obviously going to be different than the tangent line here, which is going to be different than the tangent line here. And so finding the slope at a particular point was a tricky thing to figure out before Newton and Leibniz. And if you recall from our last video, or maybe from your previous calculus lecture, basically what we want to think about is, okay, if we can't think of the slope at one point, let's just think of the slope at 2 points. And then Newton's idea was then, okay, so we'll just call the distance between the 2 points delta x, the change in x, because it's kind of like the distance that I'm going over. And we're just going to make that change of x go to 0. We're just going to bring this point in closer and closer to this black point. And what we saw was that this dotted tangent line basically approaches, and it doesn't basically approach, it does approach that black tangent line that we're actually trying to find. So this definition right here is what we came up with. And if we recall, literally this is just the change in y over the change in x. It's just kind of looks a little more complicated, but at the heart of it, that's what it is. And when we see this f prime, remember that just means the derivative of the f of x function. So f prime of x is just the derivative of the f of x function. So that kind of catches us up. Today I just planned on working some examples of actually how do I use this definition to get a derivative, and what does that derivative really tell me. And so let's start with a nice linear function. Now remember, the derivative is just the slope of a function, and we already know the slope of the function. For a linear function, it's going to be 3, right? I mean, for that particular one anyway. So we know we are looking for the answer of 3. So let's make sure that our definition gives us the answer that we actually know should be right. So let's do it. So we're going to take the limit as change of x goes to 0. And we'll have, I'm just going to write out the definition, I suppose. And then I'll start plugging some values in. Okay, so now I need to plug in f of x plus delta x, or change in x. But we know how to do that. You just substitute x plus delta x in for x. So it's going to look something like that. Now I'm going to subtract off f of x. Whoops, I was about to write f of x. That's not going to get us anywhere. Let's actually put in the function. Okay. So far so good. Nothing too terribly tricky right now. Let's go ahead and distribute that 3. Let's go ahead and distribute that negative across our parentheses there. Now notice we get some cancellations. For example, 3x cancels negative 3x, negative 1 cancels positive 1. And now I'm just going to work laterally here. So that's going to equal the limit as delta x goes to 0. What's left over? 3 delta x over delta x. But guess what? Delta x is cancel. Maybe I should do that in blue. It looks like I was doing cancellations in blue. So there we go. We have the limit as x goes to 0 of 3. Well, 3 is a constant function. It doesn't matter what is going on, or it doesn't matter what my delta x is doing. If it's constantly 3, it's just going to be 3. So there's my derivative. So the derivative of that function is 3. And that does not depend on the particular x value, which we know to be true, right? Lines have a constant slope everywhere, and so everything works out. It seems like our definition is working the way we want it to. So now, let's move on and let's maybe try a slightly more curvy function. So we're going to find the derivative. We're going to stick with polynomials, and I'm only going to move up the complexity ladder just a little bit. We'll try a quadratic function. Find the derivative of, let's say, f of x equals 2x squared minus x plus 6. Okay, so let's see here. We're going to go ahead and find the derivative is going to be the limit as delta x goes to 0. By the way, I like this delta x notation, but I've found that at least in the last few years, a lot of people have switched over to using h to represent delta x. I don't know, I think just the notation is simpler for people whenever it's just one letter instead of that Greek letter followed by x. And so, you know, if you have a calculus class that you're working through, you're using these videos just to help, you guys might be using h's here, and that's fine. Obviously, it's just a difference in notation. It's not a conceptual difference. It's not like a mechanical difference or anything like that. It's just notation. So you feel free to swap x's in here if that's what you use in your own class. So now all I'm doing is I'm plugging in x plus delta x anytime I see an x here. I'm just doing this part of the definition. Okay, and so now I'm going to subtract off the original function. And then, of course, is all delta x. Okay, so maybe I should color code this. This right here is this right here. And then this right here is this right here. And the rest is just coming from, you know, our definition, just kind of our template, I guess you could say. Okay, so maybe I should go ahead and square out that binomial. That seems like the next logical step. And I'm going to maybe kill two birds with one stone, and I'm going to go ahead and distribute that 2 throughout the quantity as I do this. Okay, so that's this thing squared out and then multiplied by 2. Then I'm going to have this negative, so it's going to be minus x minus delta x plus 6, so I'm right there now, minus 2x squared. Now I'm going to distribute that negative throughout the quantity. So that turns into a positive, that turns into a negative. This is all over delta x, but we have some cancellations. So let's see here. 2x squared is going to cancel negative 2x squared. Plus 6 cancels minus 6. Minus x cancels plus x. Notice that everything left has a delta x factor. If I'm doing the definition of derivative on a polynomial, that's the way it should work out. Once you get done with your cancellations, all that remains in the numerator should have a delta x factor in it. That's kind of an important pattern that we see finding the derivative of polynomials in this way. And again, I'm going to go ahead and work laterally. Notice that since everything in the numerator has that common factor, I could factor out that common factor. So I'm going to factor out delta x. And I'm just going to have 4x plus 2 delta x minus delta x. So all I did was factor out a common factor of delta x, and hopefully we can see why that's useful, because now I can cancel my delta x's. And so now I'm not going to get division by 0 in the denominator. Now I'm going to have a nice, easy limit to compute. Let's take the limit as delta x goes to 0 of the expression that's left. It's going to be 4x plus 2 delta x minus delta x. Oh my gosh, I made an error. Look at this. If I have delta x here and I factor out delta x, I'm just going to have 1 left over here. So actually that's just 1. My mistake. Okay, I guess that's a good reminder to be very careful with these. There's a lot of steps and there's a lot of expanding and canceling. It is easy to miss things like that, so do be careful as you do it. Okay, so I can just plug this in. This is a polynomial, right? So if I plug in 0 for delta x, obviously that term goes away, and I just get 4x minus 1. So the derivative of f of x, and remember that's what this notation means, the derivative of f of x, is just 4x minus 1. So what does that tell me? Well, what that means is the slope of that curve, which we know it's a parabola since it's a quadratic function. So the slope of that function is given by this expression. And obviously, since it's a parabola, something like that, right? The slope depends on where you are on the x-axis. And so if I wanted to know the slope of this function, and again, remember, I'm kind of being loose with the language here. When I say the slope of the function, I mean, pick out a point, draw a tangent line. What's the slope of that tangent line? That's really what I mean. But if I wanted to do that for, say, I don't know, let's say we wanted to know the slope right at x equals 3. Well, this expression tells me what that slope would be. I would just plug in 3 to my prime function, my f prime of x. So let's do it. F prime of 3 would be 4 times 3 minus 1, which is equal to 11. So I would have a slope of 11, which is a pretty steep slope, right? You're going up 11 units for every 1 unit you go over. If I look at x equals 3, that would be my slope. I think it might be beneficial right now to jump over to Desmos and actually look at this function and see if this derivative actually makes sense. Okay, so I had 2x squared minus x. Was it minus 6 or plus 6? I kind of forget. Let's see. Just scroll back up real quick. Plus 6. Okay, ooh, up here. So this is saying if I type in x equals 3 and I look at that tangent line, I should have well, that makes sense to me, doesn't it? I mean, that's a pretty steep part of the graph. Okay, so let's see here. Let's pick something over here. Let's maybe pick -1, because we could clearly see that the slope should be negative at -1, right? That's definitely a downward slope there. Now let's see if that's what our derivative actually does give us. So f prime of -1 would be 4 times -1 minus 1, which is -4 minus 1, which is -5. And just looking at the graph, that seems reasonable. That's a pretty steep slope, and it's definitely negative. So it seems like this expression is giving us correct values. So I think it's important, obviously, to be able to compute derivatives. I mean, that's one of the main things you'll do all semester. If you're taking a high school course, it'll be all first semester pretty much. If you're in college, it'll be the first half of the class. You're basically just doing derivatives all day, every day. So it's obviously important to compute it, but you need to know what that expression is really telling you. Once you get done and you say, okay, well, here's my answer, you also need to know, well, what does that really mean with regards to the original function? And it's a expression that tells you for any given x value what is going to be the corresponding slope at that point. So it's good to be able to do both. In the next video, I plan on working a couple examples where we're going to find the derivative of things that maybe aren't polynomials. Polynomials kind of have their own flow to them, but things that aren't polynomials, sometimes we have to work in some extra tricks, and I want to show you a couple of those. But I think with only 2 minutes to go, I don't have time for another example, so I'll see you next video.